Hello, welcome to Astronautics for Exploit. This is Dr. Anyeshola Ogundele. Planetary Defense Strategies. The focus points of my presentation are as follows. Near-Earth objects, near-Earth object tracking, planetary defense, and planetary defense missions. Over the years, planetary defense ability to detect near-Earth objects, such as asteroids and comets, that might pose danger to the Earth, to provide warning in case of the possibility of occurrence of the danger, and to provide the means to mitigate their possible effects, has gained tremendous attention from the researchers, space agencies, governments, and planetary societies. A near-Earth object, any small solar system body whose orbit is within the proximity of the Earth, is considered to be a potential hazard object if its orbit crosses the Earth's orbit and is larger than 140 meters across. Near-Earth objects are characterized so as to determine their orbit trajectory, size, shape, mass, composition, rotational dynamics, and a host of other parameters. The characterization will help to determine the severity of their potential impacts on the Earth. Various methods have been proposed by the researchers to deal with the dangers that deadly asteroids might have on the Earth. Examples are by changing the asteroid directions and redirect their orbits using gravitational pull of a spacecraft, and by turning them into vapors using lasers. Once a dangerous asteroid is detected on time, then a mission can be launched into space to deflect the asteroid. Using radar tracking data, near-Earth objects observers can more precisely determine the orbital path of an asteroid and predict that path towards the future. Research findings show that using radar system gives a possibility of a better and precise determination of asteroid orbits than using optical telescopes. Presently, there are ongoing planetary defense missions, and future missions are being planned. Examples of such missions are NASA's Double Asteroid Direction Test Mission and ESA's ERA Planetary Defense Mission. The Double Asteroid Direction Test, a robotic probe mission that will travel through Deimos and Dimorphos, and whose target is Dimorphos, is the humanity's first ever attempt at changing asteroid orbit, and it is designed to assess the feasibility of deflecting potentially hazardous objects away from the Earth. The ERA Planetary Defense Mission, the first probe to rendezvous with the binary asteroid system, is designed to examine the aftermath of the first kinetic impact test of asteroid deflection. ERA will perform a detailed post-impact survey of the target asteroid Dimorphos, the orbiting moonlet in the binary asteroid system known as Didymos. Near-Earth objects. A near-Earth object is any small solar system body whose orbit brings it into proximity with Earth. If a near-Earth object's orbit crosses the Earth's orbit and the object is larger than 140 meters across, it is considered a potentially hazardous object. Most known potentially hazardous objects and near-Earth objects are asteroids, but a small fraction are comets. This picture shows an artist's impression of a near-Earth asteroid. There are over 29,000 known near-Earth asteroids and over 100 known short-period near-Earth comets. It was widely assumed that collisions in the past have had a significant role in shaping the geological and biological history of the Earth. The near-Earth asteroid 433 Eros was visited by a probe in 1990s. Larger asteroids penetrate the atmosphere to the surface of the Earth, producing craters if they impact a continent, or tsunamis if they impact the sea. Interest in near-Earth objects has increased since the 1980s because of greater awareness of the potential danger. Near-Earth objects have low surface gravity, and many have Earth-like orbits that make them easy targets for spacecraft. This picture shows near-Earth comet Hadley 2 visited by the space probe Deep Impact. Near-Earth object tracking. A tracking radar is used to track and measure the coordinates of a target. It provides data which may be used to determine the target trajectory and to predict its future position. The functions of tracking radar are detection of target, determination of target range, elevation and azimuth angles determination, and determination of Doppler frequency shift. This picture shows asteroid detection radar dish antenna system. New observers. Using radar tracking data, new Earth object observers can more precisely determine the orbital path of an asteroid and predict that path out years into the future. Observing an asteroid for less than an hour with radar will provide a more precise determination of the orbit than months of observations from an optical telescope. This picture shows radar image of asteroid 2004 made by the Green Bank telescope from radar transmitted from Goldstone Deep Space Network antenna. First radar observation. Since the first radar observation of the asteroid 1566 Icarus in 1968, the radar powerful technique has been used to observe passing near-Earth asteroids and comets. Recent radar measurements of the potentially hazardous asteroid Apophis helped eliminate any possibility of it impacting Earth for the next 100 years. This picture shows asteroid impact mission. Arecibo Observatory Telescope. Of all the asteroids observed by the Planetary Radar, over half were observed by the large 305 meters telescope at Arecibo Observatory in Puerto Rico. The radar images of 2016 AJ-183 asteroid revealed considerable detail on the object's surface, including ridges, small hills, flat areas, concavities, and possible boulders. This picture shows illustration of the impact of the dart projectile on the binary asteroid system. Planetary Defense. Planetary defense encompasses all the capabilities needed to detect the possibility that one of potential asteroid or comet impacts with Earth, and then either prevent them or mitigate their possible effects. This picture shows an asteroid showering on the Earth-Moon system. Planetary defense involves finding and tracking near-Earth objects that pose hazard of impacting Earth, characterizing the near-Earth object to determine their orbit trajectory, size, shape, mass, composition, rotational dynamics, and other parameters. This picture shows illustration of space situational awareness to detect, predict, and assess threats from space and their potential risk to life. Planning and implementation to measure to deflect or disrupt an object on an impact course with Earth, or to mitigate the effects of an impact which cannot be prevented. Also, the new effect mitigation implies measures that can be taken on Earth to protect lives and property, including evacuation of the impact area and movement of critical infrastructure. This picture shows Hayabusa 2, Japan's Hayabusa 2 mission to asteroid Ryugu. Near-Earth object characterization. Near-Earth objects are characterized based on the reason to determine the severity of the potential impact event, to one of its timing and potential effects, and to determine the means to mitigate the impact. This picture shows asteroids Benin and Ryugu, Both the 525 meters diameter Bennu asteroid, visited by Osiris, and 1 km diameter Ryugu asteroid, reached by Japan's Yamazu-2. Planetary defense missions. Different missions have been sent for planetary defense and also been planned for the future. And some of them are Double Asteroid Redirection Test Mission and ERA mission. Double Asteroid Redirection Test Mission. NASA's DART spacecraft is the world's first planetary defense test mission. It was launched in November 2021. Double Asteroid Redirection Test is aimed at testing a method of planetary defense against near-Earth objects. This picture shows illustration of that Double Asteroid Redirection Test mission colliding with the smaller body of the Didymos binary asteroid system in an attempt to measurably shift its orbit. DART's mission design strategies are to deliberately crash a space probe into the minor planet moon Dimorphos of the double asteroid Didymos to assess the future potential of a spacecraft impact and to deflect an asteroid on a collision course with Earth through a transference of momentum. This picture shows artist's impression of the Melami CubeSat carrying out one of its main tasks of studying asteroid dust particles. DART kinetic impact approach. The DART mission plans to shift an asteroid's orbit through kinetic impact, specifically by smashing a spacecraft into the smaller member of the binary asteroid system Didymos. The asteroid Didymos poses no threat to Earth. It was just taken as selected for the test. This picture shows artistic impression of DART spacecraft. DART as an impactor. The DART spacecraft is an impactor with a mass of 610 kilograms that holds no scientific payload and has only sensors for navigation, such as the sun sensor, star tracker, called Smart Nav software. This picture shows DART spacecraft and Pegasus launch vehicle attached underneath Albedo L-1011 aircraft. ERA mission. ERA is a planetary defense mission under development. This picture shows illustration of ERA planetary defense mission. ERA will render for in the late 2026 December with the binary asteroid 65803 Didymos, and in particular its moon Dimorphos, which will be impacted by NASA's DART spacecraft on 2022 September 26 as the first asteroid deflection test. This picture shows ESA's ERA mission for planetary defense approaching the Dimorphos asteroid moonlet. ERA main goals are characterization of the physical properties of Didymos and Dimorphos and of the crater made by the DART mission, and also measurement of the momentum transfer efficiency resulting from DART's impact. This picture shows ERA mission for planetary defense being designed to survey the smallest asteroid ever explored. ERA planetary defense mission will be the first probe to render with the binary asteroid system to examine the aftermath of the first kinetic impact test of asteroid deflection. This picture shows the Juventus CubeSat to be delivered to the Didymos binary asteroid system. Post-impact survey. In the world's first test of asteroid deflection, ERA will perform a detailed post-impact survey of the target asteroid, Dimorphos, the orbiting moonlet, in a binary asteroid system known as Didymos. This picture shows double asteroid direct mission impacting on the asteroid Didymos. Moonlet. Once that mission has impacted the moonlet, ERA will turn the grand-scale experiment into a well-understood and repeatable planetary defense technique. This picture shows Apex CubeSat over the smaller of the two Didymos asteroids. The era mission for Planetary Defense being designed to survey the smallest asteroid ever explored. Binary Asteroid System, demonstrating new technologies from autonomous navigation around an asteroid to low-gravity proximity operations. Hera will be humankind's first probe to rendezvous with a binary asteroid system. This picture shows Didymos and Didymon with its proposed Hera mission. For more information, contact Astronautic for exploits. You've been watching and listening to Planetary Defense Strategies, presented by Dr. Anyanshola Ogundele, with the focus points near-Earth objects, near-Earth object tracking, planetary defense, and planetary defense missions. Thank you.